Okay, good morning everyone. Again, I'm Manoj Karkee from Washington State University, associate professor there working in agricultural engineering. My background might be slightly different than most of you over here. I'll try to speak in relation to pest management, but it may not be 100% in that area just because I'm from a slightly different background. If you have any questions anytime, you can stop me or write me or give me a call or anything you would like to do. There should be contact information somewhere in the system. Okay, with that, I'll be talking about UAS or UAVs and its application in agriculture with some emphasis in pest management. This presentation was contributed a little bit by Dr. Lockhart, Dr. Jack Litzman, Dr. Shankaran, Dr. Taylor, and Dr. Zhang, all from Washington State University Center for Precision and Automated Agricultural Systems. I'll take a moment here to introduce our center, hoping that will be helpful. If you have any questions or would like to know a little bit more about a few different areas of research and development that's occurring at Washington State University Center for Precision and Automated Agricultural Systems. This is located in Prosser, Washington, directed by Qin Zhang. About 15 faculty members working in this center come from different disciplines such as extension education, socioeconomic analysis, horticulture, other biological systems or biological sciences, and engineers as well. Facilitates collaborative systematic research in agriculture, including precision agriculture, robotics, automated agriculture, and such. A few projects to list here: apple and cherry harvesting, apple and raspberry pruning, intelligent bean transportation systems. Among all those projects, we also have a big emphasis on UAS or UAVs for production agriculture. So, unmanned aerial systems. I'll start with a little bit of background. For some of you, it may just be a quick refreshment. For some of you, maybe it still has some information there. Unmanned aerial systems, we also call them unmanned aerial vehicles or drones. Aerial systems is what generally we use in FAA rules and more scientific communications. It is a system because it includes hardware platform like fixed wing or multi-copter platforms that fly. It includes communications and navigation. It includes a lot of control, sensing, decision making, all those components, and that's why it is a system. In terms of sensors, that's where our main interest is in terms of agricultural applications. We use different types of color cameras, laser, multispectral and hyperspectral cameras, thermal cameras, all those to monitor crops, detect different parameters of the crop, and link it to some way we can better manage crop, whether that be dealing with different types of pests or understanding different types of nutrient stresses and such. This system also includes data processing, storage, and distribution, and more importantly, conversion of data into knowledge, because it's not always, we may have tons of data, and we certainly do, using all the different kinds of sensors and platforms and connected sensors over there. We collect a lot of data, but it doesn't always translate to what we can do with it. The translation from data into what we call information or knowledge that can be acted upon. And that's a big part of unmanned aerial system. Before again we jump into some applications, I want to give you a sense of different scale of UAVs in terms of platform. I'm using UAV here because I'm just talking about platforms. It could be as tiny as a bee. I think a group in at MIT developed a little bee-size UAV to perform operations such as pollination and many other applications that could be possible with an insect or insect-sized UAV. And it could range anywhere from there to a few pounds to several pounds to dozens of pounds to hundreds of pounds to something like a let's say Airbus 380, that passenger airliner. So the UAV can range from in between anywhere of these two extremes. Our interest in agriculture, though, is in oftentimes more towards the micro to small scale UAVs that would range from several pounds to tens of pounds. Sometimes we are also interested in platforms like this Yamaha platform, a few hundred pounds. But again, in terms of monitoring and stress evaluation and other applications related to remote sensing, we are okay with platforms that weigh about 5 to 10 to 15 pounds. This industry, UAS industry, is making a lot of economic impact. It also can be seen in the changes in spending at the Department of Defense. In 5-year period from 2005 to 2010, their spending in unmanned system compared to manned systems, that ratio changed substantially, as we can see, from about 5% to 41% in unmanned system within that 5-year period. This went up from a few $100 million to several $1 billion over that period. So that shows how fast the spending at Department of Defense is moving towards unmanned system than manned system, more towards drone, let's say. Agriculture has a big potential to make a huge economic impact in aviation industry using unmanned aerial systems. Here is a report that shows that in next 10 to 15 years, the agricultural applications of UAS or economic impact of UAS would increase dramatically, and that would be far beyond the size or the contribution from public safety and other sectors of UAS. So that shows a big potential for growth in agriculture in terms of economic impact of UAS. Down here we see a few states that are making or are going to make the biggest contribution. California being on the top, Washington and Texas following California. You see the numbers here again. This is in terms of job creation impact and an economic impact. Bottom line, UAS is big and going to be even bigger very rapidly over the next 10-15 years. In terms of its application in agriculture, I generally argue that this is prime time for agriculture because of the potential that UAS brings us in agricultural applications. In one word, or one sentence rather, we're going from plot scale or field scale to plant scale, at least in terms of capacity of these systems. Precision agriculture is best, or is in its best condition if we can manage individual plants for anything that plant needs, rather than looking at a few acres at a time or even grids of 10 meter by 10 meter. We had the best precision agriculture when everything was manual. We would be managing one corn plant at a time 200 years ago, or whenever it was. But with big machines and everything, we did a lot of progress but the precision egg lost its resolution. But with UAS, we have this opportunity again to go back, look at one plant or a few plants at a time, and manage them with precise application of chemicals, nutrients, and any other management that we need to do at plant level, which would be the true precision agriculture. Again, this is potential that is coming there. Whether that makes economic sense or not, that's a different story. We can discuss a whole lot about that. It may take time to actually implement that kind of concept, but it's a prime time because UAS provides us that opportunity to sense and manage individual plants. With that, let's talk briefly about potential for pest management. There could be several areas where UAS technology could be applied. I generally divide these applications into two categories: passive applications and active applications. By passive, what I mean is that UAV is flying over something and passively recording something or sensing the environment. It's not doing anything. There is no action in terms of changing the input or controlling anything in the field. The sensor itself could be active or passive. I mean, by active sensor, we mean we generate some signal and receive it back, like a laser scanner. A passive sensor would be like a color camera. We just record whatever reflectance comes out of the ground based on sunlight. So sensor itself could be active or passive, even though the application is passive. And when I say active application, it includes something that this UAV or UAS is doing in the field. For example, applying some chemical or chasing birds from crops like blueberries and cherries. So there are a lot of different possibilities within both active and passive applications of UAS, including certainly pest management aid with this technology. There are a lot of ongoing engineering efforts in bringing this technology down onto the fields and making sure we do something good with this technology that makes a positive impact to the industry, or bring this technology down in a way that growers can use it or crop consultants can use it and make, again, a positive impact to the industry, whether that be improving the efficiency, managing the stress in timely fashion, improving the crop yield, ensuring crop quality, whatever that is. We want to develop a few engineering technologies, data processing technologies that has those kind of implications to end users. One set of applications that we are exploring with UAVs, researchers around the world have been exploring with UAVs, is to validate applications with proven values. I mean, we've been using remote sensing for decades, using satellite sensors, manned aircrafts, ground-based sensors. We have been collecting a lot of data, images, for, again, half a century or more specifically. But we want to try that with UAVs. These are smaller platforms, mostly, they're much less stable compared to a manned aircraft. We want to use this technology and prove or validate these proven technologies such as color and NDVI maps, which shows us some kind of a difference, spatial or temporal difference in crop conditions, plant stress maps, precision chemical application. Again, these are the technologies we already have, but we want to validate with UAVs. And we want to also develop new or emerging applications with the potential that this technology brings to us. And it might include identification of new particular disease such as citrus greening disease. And again, bird deterrence comes up again and again because that's one application that I'm exploring myself in my research program. The next aspect of all this is what we call technological development, where we'll be looking at increasing the stability and endurance of a platform, like a little multi-copter or a little fixed-wing UAV. Why is it important? Given current technologies, for the type of platform we use in agriculture, we're flying 10, 15, 20 minutes at a time because these batteries do not last very long. That's a very critical challenge there, and there has been studies in technological development so that we can increase that endurance, whether that be through automatic battery swapping or through the use of fuel cell or some other aspect so that we can increase that time in air from 10, 15, 20 minutes to several hours to even several days. Improving image stitching, new data mining, those technologies are also important so that we can again convert data into knowledge. So a little bit again in terms of remote sensing potential with UAS. As I indicated earlier or mentioned earlier, remote sensing could happen many different ways: fixed platforms, ground vehicles, satellites, aerial, that could be manned and unmanned. But unmanned aerial systems bring us a few unique potential or opportunities that other platforms did not have there. That includes higher resolution data. Again, we could go to plant scale now. Certainly in perennial crops like apples, we can very easily identify individual plants and their health conditions or stress conditions using UAS even now. But I'm thinking it may bring us even down to single plant for even corn or some other crops. More frequent flights, safer operation, flexibility and maneuverability, and low cost. These are some of the potential opportunities or benefits that UAS brings to us in terms of remote sensing compared to our traditional or conventional tools such as satellite images or images from a manned flight. So with that, we could do a lot of things with remote sensing. First, let's talk about monitoring for pest management. Using the sensor like this, or a platform like this is a EB sensor, platform. We could map, for example, canopy variability or plant stress variability and monitor effectiveness of pest control strategy. For example, there is a potato field and some part showed some stress. You applied some treatment, whatever that is, whether you added more nutrients or you identified certain pest and you applied some pesticide, and you want to see over time if that chemical helped or not. And you could go back repeatedly to that plot and collect data, analyze it to see if there has been any improvement, whether the area that was stressed has now recovered or not. So there could be that potential with UAS and real-time monitoring for field management. The application could be as simple as, which all of us know, rather than having a field manager drive through plots again and again every day or several times a week, we might just send a little UAV, collect simple color images so that these field managers or crop managers would simply go to the areas that shows some problem rather than scanning everywhere. So this could be the application as simple as that. And based on my communication with farmers, I have heard that simple application like that could improve the efficiency of managers by 50–60%. Again, you guys are more experienced in field management than I am, but those are the numbers I've heard from apple and cherry growers in Washington. Let's talk about a few examples. One example our program at Washington State University is working on is detecting vine vigor. Washington State is quite big in wine grapes these days. It's increasing quite rapidly, and certainly it's not the Napa Valley, but it's becoming second Napa Valley. If you go look at the numbers, they're vastly different. We're talking about 95% to 5% in that range, but still Washington is there in the map and getting bigger. And because they're planting or expanding their plantings very rapidly, it brings us problems such as may not be planting in right location, right soil condition, whether that be the slope aspect, other aspects of site selection may not be perfect. So there are a lot of variabilities in vine vigor. And mapping that vigor would tell the farmers where the potential problem might be, so that they can focus on those areas and correct it. So using UAVs or UAS rather, we could convert these images into some sort of vine vigor variability map that would then help growers do something about it. Another application we're working at Washington State University is in monitoring the efficacy of subsurface microirrigation. Applications in again wine grapes and cherries and some other crops at Washington State. Just to bring you up a little bit in the speed, all the crops grown in our region of Washington are irrigated because we get about 7 to 8 inches of rain every year. It's basically a desert. So irrigation is a very important challenge in the crop production in eastern Washington, and that's why we're trying many different ways of irrigation to improve efficiency as well as precision. We don't want to apply more water than necessary because, as we know, more water doesn't always do good. And also we want to be using less when possible. Now they are developing this what we call subsurface microirrigation system, and we're using UAVs to monitor these crops to see where there is still lack of water, or if there is any problem with the micro subsurface emitters. Because if there is a blockade in that little emitter that is under the soil, there would be no moisture in that area, and the UAV with certain sensors like thermal camera would be able to tell us the difference between moisture conditions over the space, and that again would tell us a few things, whether there is problem in applying water or we're applying too much water with this kind of new irrigation technologies. One example from University of Florida in HLB or citrus greening disease, using UAVs and different types of sensors such as multispectral camera, they were able to detect the plants with this disease. For example, you can see D, D, and H for healthy. This looks really scary map already, and as we know, I think about half of the plants or trees are already in problem with this disease, and it's always increasing. USDA has even a separate SCRI, the Specialty Crop Initiative Program, to help manage this disease in Florida and other parts of the country. But anyway, this team from University of Florida has developed a UAV-based technology to detect this disease so that we could do something about it. That something could be many different things they're trying. One thing they're trying is to use thermal treatment, heating these trees to get rid of or reduce the effect of HLB disease. And this UAV is helping the growers to find where the problem is and bring their heating system to those locations to treat those trees that are infected. Another application that my program at Washington State University is looking at is to deter birds with UAVs. Bird is a big challenge. Most of you might already know it. Particularly, there are certain types of birds which might be migratory birds, but there are some local birds too that damage a lot of ripe fruit, particularly in blueberries, apples such as Honeycrisp apples, wine grapes, and cherries. If they focus on one fruit and finish eating it, maybe it would be okay. But what they do is they pick one fruit and then move to next and to the next, rather than eating a whole lot out of single fruit. And in some cases, we are told that in some of the worst years, these birds can damage as much as 50% of crop in certain locations. Certain locations which are, let's say, closer to the wild shelters for these birds, closer to creeks or forests, these birds are really challenging for farmers. They're trying tons of different ways, even using netting. The two, either these technologies are not effective or very, very costly. Netting is a good solution. It may help, but it is highly expensive to net hundreds and hundreds of acres or even thousands of acres of crop. And that's why they're looking for new innovative solutions. And our hypothesis is that UAV can do it through two things. One is automated detection of where the birds are without a human being involved in finding where they are, and then sending these UAVs to those locations using different sounds and flight patterns and other assistive technologies so that we can scare them off. Some of the birds of our interest in terms of chasing away, based on our field experiments. Our collaborators at Oregon State University tried to use it last few years, and they got some data, but it's not conclusive whether this works or not. And at Washington State, over the last 2 years, we're trying a few different types of platforms and different types of flight patterns to see how effective we can be, and it's showing very good promise right now. We use both what we call fixed wing and multi-copter platforms. Fixed wing can go faster and can be turned into something. It looks like a predator bird, which might be more scary to some of these birds. On the other hand, multi-copter platform can go to the problematic areas and hover above it and make a lot of noise to scare them. So they have their own pros and cons in terms of chasing birds. So a little video. It's not as effective without sound here, but we can see some birds flying away. There is a UAV hovering on top of it, which we cannot see here. If we had sound also playing right now, then we would be able to see it. So what we're doing here is that there is a multi-copter or quadcopter flying, we see it now, on top of these canopies, and it scared those birds out of those canopies. So we use remote controlled flights to see if we can do it, but eventually our goal is to do it automatically. We would not have to, a human operator would not have to be there finding where the birds are and sending the UAV there. Rather, we would like to do it automatically, and for that purpose we developed, or we are developing, an algorithm that would automatically detect if the birds are coming into the field and then send a UAV to deter them. So this little video here shows us automatic tracking of birds using cameras. So those lines there, you see, when birds are moving from one direction to the other in this space, we are able to track them. Not with 100% accuracy, but it's quite close. That pink line there is just an arbitrary imaginary line like we see in football fields showing the yard line. But it's kind of a boundary we're looking at, and if anything goes past that boundary, we don't care, and if they want to try come inside that boundary, then we'll be sending our UAV to scare them. So another application we're looking at with UAVs is using this what we call Yamaha platform to prevent from cherry cracking problem. In cherry crops, if there is a rainfall event just before this or around the time these crops are ready for harvesting, due to a lot of moisture in the fruit, it starts to expand and crack. And growers these days use manned helicopters to go there and then shake off the excess water from this fruit, which is very risky, and every year there are some accidents happening in cherry growing regions. In Washington state alone, there are some fatal accidents over the last 5-6 years, and that's why growers are very interested in seeing this kind of unmanned systems that could potentially replace or at least complement manned flights when the flights needs to be very low, closer to canopies, which is risky or dangerous for manned flights. So using this technology that has been used in other parts of the world quite extensively, like in Japan, where they use this in very high numbers, as we can see from this graph. Washington State University is trying and showing very good promise that this can achieve similar effectiveness in drying cherry crop using this unmanned Yamaha platform, and can be very effective. We still have a lot of regulatory and other challenges to get it to practical application, but from the research perspective, is showing a good promise. There is I'll talk about it in a little bit, but there is a very good research going on at University of California, Davis, in terms of using this platform for precision spraying or automated spraying. This picture I got from this web page here shows one of those, I think, research trials that University of California at Davis did in terms of what we call surgical chemical application in wine grapes. By surgical, what I mean is that this platform is used to only go to a little problematic area and apply these chemicals in a very precise or localized way, rather than replacing tractors that are applying or broadcasting chemical all over the field, which might not be very effective with this kind of platform, because fields here in US are very, very big compared to Japan, where this platform has been very popular actually to apply chemical in entire fields, because fields there are 20, 30, 40 acres towards their larger size. Here we're talking about, again, several hundred to thousands of acres. So it's a different scale, but it's still very effective in terms of what we call surgical chemical application. Now, past those applications, there are different research and development activities going on in terms of technology development. I started with a few challenges in the technological aspects of UAS. Platform stability, weight, speed is one area, because when we're flying, we want to be very stable, even in the condition of certain wind and other factors, and that requires a lot of aerodynamic studies and control system studies, so that this relatively small platform, lightweight platform, can still remain stable, relatively speaking, on the air. Multiple vehicle coordination and fleet size optimization. If we were to bring this technology to the field, again, several hundred or thousands of acres of fields, then we're for sure going to use more than one. It could be dozens, maybe even hundreds of these platforms working simultaneously in the field. So that requires a lot of research and development in the area of what we call coordination and collaboration between these individual units. We don't want to hit each other, and we don't want to overlap their working space. At the same time, we don't want to leave certain area in the field not covered, whether that be monitoring for strays or chasing birds or whatever that is. We want to cover entire field with multiple of these platforms, but also want to be very efficient, not to overlap and interfere with the operation of others. So that requires a lot of research and development, which is happening in the technological development space of this technology. Charging station is another area where there has been a lot of research already in place with good results. New power sources such as hydrogen fuel cell. One of our faculty members at Washington State University has demonstrated the use of hydrogen cell in a platform that was developed in-house, which shows an endurance of about 24 hours rather than 24 minutes with the existing batteries. New sensor for agriculture. We want to be developing very lightweight, target-specific sensors, whether that be to detect HLB disease or some other issues in the field. For example, here is a battery swapping station developed by Taksas et al. In 2011. Automated battery swapping is easier with multi-copter or platforms which can hover and go slowly and land where we want it to be landing at. It will be much more complex and challenging for fixed wing platforms that are landing at some speed, but there are some research going on in that direction as well. I talked about hydrogen cell research at Washington State University. This is the platform they used. Again, this was developed at Washington State University by the team of Jacob Litzman. And again, they're showing that this platform can fly now 18, 20, 24 hours a time using a small hydrogen cell to power this platform. I'll take another 5 minutes or so before opening up for questions and other aspects of this session. But let me talk a little bit about, or kind of summarize the challenges we discussed so far and a few potential future research and development that might be happening in coming years. I started with this and I want to conclude with this. Collecting data is the simplest possible thing we can do with UAVs or any other type of remote sensing devices. But how we use it, how can we use it to make a positive impact, to help growers make some timely decisions, right decisions or informed decisions, it's a big challenge. We've been doing remote sensing for, again, more than half a century. But it hasn't picked up a whole lot in terms of its practical application because we have always had this challenge of converting what we collect into what we can use. We generate a lot of NDVI maps, normalized differential vegetation index. It shows some difference. Well, here is relatively healthier plant. Here is not so good. That part is the worst. But we don't know what is causing that problem in that area. We see there is a problem, but we don't know what that problem is. So converting from this, what we see, into what it is and how to deal with it. Connecting that dot, for example, from sensor to, let's say, a tractor that would, or a sprayer that would apply certain chemical to certain part of the field or certain tree is a big challenge. And that's where we have research and development going on, and it needs to go on to make sure we can effectively use these platforms. Another aspect of it is connectivity and integration, which is already happening a whole lot. Every devices we carry these days is connected to some extent, but this will keep growing in the future. Everything that's there in the field is connected to some common database, perhaps in the cloud, talking to each other, sharing information. But that also makes everything complex, and a lot of data mining, decision support tools has to be developed so that we can effectively and efficiently use all these connected devices to make, again, field level decisions so that eventually we get the quality and yield out of the agricultural products and agricultural industry fields that we have. Connectivity may include in the future satellite sensors, manned flights, all these things that we discussed, and ground vehicles such as chemical applicators. But again, there is a lot of research that needs to happen in this area. Innovative application and approaches. Well, we talked about a whole lot of application that is possible with UAVs, but we have not quite started to explore the potential of this platform that brings a lot of potential for very high resolution data, both what you call spatially and temporally, and perhaps at low cost. So we need to think outside the box and see what we can do with it. For example, precision pollination could be one area where we may be able to, like the bee UAV we talked about earlier, we may be able to go to individual flower and perhaps pollinate as desired, so that we could select the best flower, pollinate it at the best time, so that we have the best crop out of it. For example, in cherry or stone fruit, where it's a mass pollination and we have to thin a lot of it so that we have only desired amount of crop in the trees, so that we get the quality and yield we want. Rather than doing all of that, maybe we want to go at right time and pollinate only right flower so that we don't have to do any crop load management after that. But again, that's an example. Could be many other examples we might think in the future to exploit this potential. Multi-purpose platform. If we were to be very effective in terms of using this resource and make economic sense to us, we might have to use it for multiple things that we do in the field. For example, collect data while chasing birds and use the same information or data to convert into whatever information or knowledge we want to get out of it. And economic analysis with those multi-purpose platforms. Transdisciplinary approaches. As an engineer, I can devise a tool that does something in my mind might help growers, but I have no idea in terms of what is really important to growers. Maybe biological scientists or horticulturists or crop scientists have other aspects of it that might help me develop a better system. Growers have their own experiences, knowledge that might help us, again, bring everything down to what they want. There could be socioeconomic scientists that might help us how this technology could be adopted so that it doesn't make a whole lot of disruption in the industry. All those aspects are important if we were to develop any technology that can be practically adopted and adopted widely. Talked about it already. Platform, payload, and data processing is the key, and it's a bottleneck currently. Payload is one aspect. We want to develop or have a platform that can carry as much as possible. For example, if it's a surgical chemical application, we don't want to come back after spraying for 2 trees. Maybe we want to stay in the field and apply to as larger the area as possible. And for that, we need to increase the payload, the amount of load this platform can carry, which would be very, very, very useful to make, again, to adopt this technology for doing a lot of things in agriculture. Sensors with agricultural application in mind, and calibration and registration, image quality, all those aspects. Because these platforms are unstable in nature, it's much more difficult to mosaic 2 images, correct it for different orientation of the sensor, calibrate it for different lighting condition, so that what we see is consistent with what we saw yesterday or what we see under a cloudy day or what we see in November versus what we see in May. We need a lot of calibration and registration to make the data consistent and meaningful, and it requires a lot of research and development in that area. Potential adoption models could be in-house technology, where we might have a semi-autonomous operation. We might have platform that we fly and upload data to some consultant to process it and send us the information back. That could be one model. We could have autonomous operation within the farmer's operation itself, which includes hardware, software, data storage, processing, everything. Farmers may still need a little bit of consultancy service for maintaining the system every now and then, but that's one model. And then service companies could be another model. With that, let me take one last minute and then we'll be done. A little bit about FAA regulation for non-recreational use. It has been much more challenging, it's still quite challenging, but since this summer, FAA has finalized what they call small UAS rule, which is defined by Rule 107. With that, we do not have to go out there, apply for certification of authorization to fly if we meet certain criteria like less than 55 pounds, less than 100 feet, daytime operation, and the operator is certified with aeronautical knowledge test. There are a lot of restrictions there, but we can fly if we meet those restrictions, or we can apply for exemptions if we can safely fly and demonstrate to FAA that we can fly, for example, in nighttime. But we need some approval from FAA to be able to do that. So with that, thank you very much. And I don't know if we have time for questions or whatever else that needs to happen here, but I'm happy to try to answer any questions or comments you might have.